All right, so the plan, so lecture 4, and now we move to higher dimensions, and I want to talk about, I want to talk about this Mergelyan type of approximation, and what one does, this is how this is defined in the literature. So we have these containments, and let me just put a closure over here, and then I have either, so let me write it the correct way. So I have R K PK. And so the Mergelyan type approximation is to try and figure out a good dense subspace for this. And since this is this part, we have a fairly good theorem for this, which is the Okawe theorem. A lot of times in the higher dimensional literature, people focus on trying to show the equality of these two. I mean, we try to find conditions so that we have equality here. And then in addition to that, if we impose rational or polynomial convexity, then we also have density over there. All right, so let me just write down the definition as it appears in the literature. So we say that K has the Mergelyan property if A of K is O of K closure. Okay? And then in addition to that, if we want rational or polynomial approximation, then we ask for rational or polynomial convexity. And again, the same comment as last time, that typically, so this is quite a hard property to study, and typically, I mean, there are results out there and they either involve closures of domains or the setting that we are going to consider today. Okay? So I'm going to now restrict myself to a very special case, and sort of the motivation to consider this class of objects comes from the following observation. So this is a higher dimensional version of something that we started with this in the very first lecture. So let K be a compact set in Rn, and I view Rn as this plane. So I view this as the plane given by imaginary z equal to 0 sitting inside Cn. Okay, so I am considering a compact subset in Cn, but it's coming from a very special space, affine space. And here, now this is not a version, I mean, this is, you need a different version of the Weierstrass approximation theorem from what I stated. I had only stated it for intervals in the line. But you have a version for this, and this will actually tell you that you have sort of the best approximation that you can hope for. So we kind of want to mimic, I mean, of course, this is a very special case, but let's say that we are somehow interested in n-dimensional real submanifolds of Cn. We kind of want to mimic this at some nonlinear level. Okay, so that leads to the next definition. So a C1 smooth real submanifold M of Cn is said to be totally real at some point P if at that point the real tangent space basically acquires, no complex structure from the ambient space. So the way we write this is that the maximal complex subspace of the tangent space is trivial. Right? And if this holds at each P, we say that M is totally real. M is a TR submanifold of Cn. And so we are going to restrict our attention. This is, so keep this in mind if you're sort of trying to, I mean, this is, a priori this condition doesn't seem to have anything to do with approximation theory, but keep this example in mind. And let's make this immediate observation that for this to happen, of course, the real dimension of M can be at most n. Okay? So since you're also learning some CR geometry, I think you can do this computation. You can figure this out. You can work with these dimensions. And we'll focus on n-dimensional real submanifolds, real compact submanifolds. So here compact with or without boundary. Of Cn. And the reason I'll do this is that a lot of times, I mean, most of the results that we'll prove for, or at least state for, n-dimensional real, compact, totally real submanifolds, most of them you can generalize to totally real submanifolds of higher codimension. Okay, so they're usually a standard trick to do this. So I'm not going to make that a big deal, and we'll just stick to the case where the dimension is n. Okay, so before I sort of tie this back to what we are trying to do over here, let's look at some examples. So of course, the first example is the linear model, which I have already written over here, which is Rn in Cn. And then another good example is, so you sort of, if you take smooth curves in C, and then you just take their products, and you'll get something totally real. So this is totally real in Cn. In fact, you can sort of, I mean, as an exercise for all the previous material, you can check that this is rationally convex, and this has some bearing on what we want to say. Let me also show you some examples where, this may not hold. I mean, so for example, let's take S2 in a specific two-sphere in C2, so Z1, Z2 in C2, such that, so I have absolute Z1 square, real Z2 square equal to 1, and this is all lying in Y2 equal to 0. Okay, so the picture looks like this. So let's say that I'm drawing this in the Y2 equal to 0 plane, and so I have X1, Y1, X2. I have this two-sphere over here. And what you can check, so check that S2 is totally real everywhere except at the north and south pole, as in the picture. So except at 0, plus, minus 1. And from the picture, I mean, this should sort of be, at least the fact that you lose this feature at the north and south pole should be sort of clear from the picture, because you can see that the tangent space over here is parallel to the Z1 axis. So that's a complex subspace, both over here and here. So this is definitely not a totally real subspace over here. This is essentially the Z1 subspace. Okay, but everywhere else, you're fine. And from the point of view of computations, it's also useful to maybe write down the following way of computing. So say your K is given by n defining functions. Then K is totally real at P if, so this is how you can check it. You can look at del rho 1, which del rho n at P, and you want this to be non-zero. Okay? It's sort of also saying that the complex span of the tangent space, so if I'm working with an n-dimensional totally real submanifold, then the complex span of the real tangent space gives you all of Cn. That's another way to think about it. Okay. So my plan for today, for the first lecture, is quite simple. So I want to state the following theorem, which connects this to approximations. And there are many versions of this result. There were several people who worked on it. There were several regularity conditions that had to be considered. And the version I'm stating, I'm not entirely sure about this, but the version I'm stating is, I think, due to Harvey and Wells. And this says that if M in Cn is a C1 smooth, totally real, compact submanifold of Cn, then it has the Mergelyan property. So then C of M is O of M closure. Okay? I'm not really saying anything about rational polynomial convexity as yet, but at least this piece we have over here due to this result. Okay? This is the Mergelyan property over here. Any questions? Okay, and what I'm going to do, and I promise this is the last proof of this course, so in the next lecture I'm not going to prove anything. I sort of want you to see the local picture over here. So the local version of this, we can say something more. So we will prove the local version of this using, so, and the reason why I want you to see this technique, even though it's not very pretty, is because it's sort of typically the first thing you try to do when you try to do approximation. It's a very standard technique. So we will prove this local version of this using a technique that goes back to, I mean, it probably goes back further, but at least in the setting of approximation theory, it goes back to Weierstrass's original proof. And the proof that I'm going to show you, I mean, I'm going to sketch it out. I'll state what we are proving. So it was Weierstrass's original idea, and then in this setting, it was adapted and was adapted by, and since this is now that you are familiar with the language of CR manifolds and CR geometry, Bowendy and Treves, to achieve polynomial approximations, so local polynomial approximations of CR functions on, I don't think this word was introduced, but generic CR submanifolds. So let me just briefly mention here, I mean, after all, a totally real submanifold is a CR submanifold. It's just that the CR dimension is a constant 0 everywhere. So whatever technique we are using, that can be used to prove something more, but I'll just demonstrate it in this setting. And by the way, this, I mean, if you work through it carefully, then you will get a proof of the classical Weierstrass approximation theorem. Questions? Okay, so maybe let me state the precise statement. And then for the rest of the lecture, I'll just prove it. I mean, I'll skip some details, but I'll show you the main idea. Okay, so what is the statement? So theorem B, which is the local version. So let M be as above, and P be in the sort of relative interior of M. What I mean is that, of course, there I've allowed boundary. I'm not going to worry about that. So P is somewhere in the relative interior of M. Then there exists a neighborhood U inside M of P such that I have not only the Mergelyan property on U closure, I in fact have this very strong approximation property, which, by the way, if you remember, this implies that U bar is, or U closure is polynomially convex. Okay, so you might come across this statement that totally real manifolds are locally polynomially convex. This is what it means, that at around every point you can find an open neighborhood whose closure is polynomially convex. And remember that, yes, so we are working, I'm very much working with an n-dimensional C1 smooth, totally real compact submanifold of Cn. We will assume that the dimension is n. So just keep it simple. Okay, so proof, sort of sketch of proof. So we'll start with a simplification that you have already seen. So let me do this. I'll try to do this. Oh, I actually want to make some, maybe I'll make some remarks before we start proving this. So right. Okay, so the first one is to go from the local picture you need a bit more stuff, and what you need is you need to solve, you need to set it up correctly. You need to solve a Cousin 1 problem, which I think was introduced in the SCV overview. Okay, so I will not go through the details of this, but this requires a little bit more, which is why I wanted to focus on the local picture. Something very strong is actually true once you assume totally real. If M is CK smooth, then in fact, not only can you approximate continuous functions by something that's holomorphic in a neighborhood, you can actually approximate CK smooth functions. So M is a CK smooth manifold, you have CK smooth functions on it, and then you give it the CK norm, and in this norm, you have density of this space. So here I'm really taking the closure in the CK norm. And once again, the local version of this, so whatever recipe I give you over here, the same recipe will work for this, at least for the local version, but you just have to estimate, you have to do more estimates to figure out that that actually works. So we'll not do that. So this is very, very strong. And by the way, if you want this kind of approximation, let's say even in the C1 norm, then being totally real is actually a necessary condition. For something, okay, maybe not, yeah. It basically has to be a necessary condition because here dbar is 0, and then you're doing approximation in the C1 norm. That means dbar over here of these continuous functions has to be 0. And so that almost tells you that the manifold has to be totally real. But anyway, we are not going to focus on that kind of approximation. And then on top of that, so the next lecture is when I will talk a little bit about, so this, we are focusing on that part, the Mergelyan part. But what about, in addition to being totally real, what if I ask for rational or polynomial convexity? What I want to talk about next, in the next lecture is that in addition to being totally real, if we ask for rational or polynomial convexity, can we characterize this in some nice way? It has some nice connections to geometry, so I'll come to that. But I just want to make a comment over here. So no closed n-dimensional real submanifold of Cn, so this n is the same as this n, can be polynomially convex. So there is a topological constraint, so I'm assuming closed, it doesn't have boundary, and I will not get a chance to talk about the topological constraints for polynomial convexity, but there's a reference, there's a book by Stout which I have mentioned on the website, and I think this is section 2.3. Where he sort of outlines some standard topological constraints for being polynomially convex. So if we are looking at an n-dimensional closed totally real submanifold, it just cannot be polynomially convex, but it can be rationally convex, and there is a very nice way to characterize it. Of course, we can consider submanifolds with boundary or lower dimensional totally real submanifolds, and then we can ask these questions. Okay? All right. So let me now discuss the proof of theorem B, if there are no questions. So proof of theorem B. So we will assume, and I just want to make sure all my notation is correct. Right. So we may assume that P, whatever point we've chosen, is the origin, and this simplification has already appeared in Professor Mergelyan's course. I mean, we've seen this. This can be done. I mean, this is, I think it was an exercise, in fact. So we assume that P is 0. I'll also introduce some notation. So for me, dn delta will be the ball centered at the origin of radius delta sitting inside Rn. Okay? And what we'll assume is that M looks like x plus I gx, where x comes from, and I'll also drop the 1 when I'm looking at the unit disk. And okay, so x comes from dn for some C1 smooth G that goes from dn to Rn with and satisfies that G of 0 and the derivative at 0 is 0. So I'm looking at a picture like this, and this picture will be useful. So let's say this is dn, so this is Rn, and when I write x, I really mean x1 to xn over here. Okay, that's how I'm writing this. And what we have is, we have some picture that looks like this. I mean, okay, maybe it's a little too nice. And so this is the graph, and this is going to be M for us. And what I need to, this is P, and I need to find a neighborhood of P so that I have polynomial, I have good approximation in that neighborhood of P. That's the plan over here. Okay. So what I can do is, so I'm not going to keep track of very fine estimates because I just want you to see the main idea. So we will choose, okay, make sure that I'm doing this right. So we choose some delta naught less than 1. And we have to choose this in a smart way. And so the way that we choose it, I will sort of reveal later. I'll tell you what will determine this choice of delta naught. Okay, we're not going to make a fuss about it, to be chosen later. And so in this picture, I have dn of delta naught. And what we are going to do is, outside of this, we sort of don't care what's happening to this manifold. So we are going to cut it off. Okay, so we'll keep it the way it is in dn delta naught, and we want, so here we'll sort of cut off. So let me use the same color. We'll sort of cut it off, and we'll sort of, so we'll keep it the same here, and then we want to keep the support. And we'll forget about this piece. Okay, so this is because we only want a local result. So we will assume that G is smooth, compactly supported in Rn. The support of G is inside the initial, the unit disk, and G coincides with the earlier function on the disk of radius delta naught, where I mean the delta naught has to be chosen the correct way, and I'll mention that later. Okay, and now what we will do is, so just some more notation. So the disks are in the parameter space, but what we care about is this manifold, which is parametrized by this disk. So we let M delta simply be the graph. So, so before I introduce M delta, let G from Rn to Cn be given by x going to x plus small ig x, and m delta to simply be capital G of dn delta. All right, so remember that this is the piece that we care about, and my claim is that for some choice of delta, this is the this is a neighborhood of the origin in the manifold, and for some delta, I will basically have good approximation on m delta. So let delta be strictly less than delta naught. Okay, and I'm going to take a continuous function over here, and I'm going to approximate it. So let f be a continuous function on m delta. Closure. And we are just going to produce, so rather than produce approximations by polynomials, I will produce approximations by entire functions, and you know how to handle that from there. So the recipe goes via, you must have come across the word approximation of identity, or sort of convolution with Gaussian kernels. So that's what we are going to do over here. So what I'm going to do is, so I have this function, so I've taken some, let's see. So I have dn delta naught, and now I've taken a smaller disk over here, dn delta, and I have a continuous function over here. And once again, I can use a cutoff function that we can use a cutoff function and assume that it is compactly supported in this larger disk. Okay, so I'll keep it as it is on the disk of radius delta, and then I'll cut it off and make sure that it's compactly supported in this disk. This is just some minor thing that we need to do to make sure that our integrals are meaningful. Okay, so this is the procedure. So let f epsilon of z, and I'm sure you've come across these kernels before. So I'm going to, this integration is going to take place on m delta, correct. So it can take, doesn't matter, so it can take place on m delta naught, and you have f of w, you have some constants that are going to make all of this work, and then you have this Gaussian kernel, which I will have to explain to you, because remember that I'm working with an n dimension, okay? So this piece has to make sense, and then I'm integrating against dw1 wedge dw n over here. And when I write z square, I really mean, I really mean z1 square plus all the way up to zn square, which I will also write as sort of the pairing between z and z. That's what we are going to do over here. Okay, so let me sort of tell you how is this going to work. So we're just going to do a little bit of computation over here, but I'm not going to fill in all the details over here. So let me make sure this is all correct. So we have this, this, and this over here. Okay, so what's happening is that note that when I take, and where do we want this z to come from? Remember, we want entire function, so the z is coming from Cn, and in fact, we do have an entire function in z over here. And so this is going to be our sequence, or really the approximants for f. And what we want to show is that if we do actually take z from the closure, from m delta closure, we want to show, so let me say what we want to show. That limit, and this is not, at first this may not seem like the correct statement, is equal to f of z for all z in m delta closure. That's what we want to show, but we want uniform convergence over here. So we need to make sure that the estimates that we do not depend on z. So when you actually sit down and go through this proof, this is the piece that you have to be careful about, because this is just pointwise convergence. But when you start estimating, you will notice that you're actually not using anything special about z, and that is where this choice of delta naught will play a role. So I'll sort of not make that very clear. Okay. So what is roughly going on over here? So this is the important piece over here. W is capital G of some x. So x is coming from d and delta naught, which is x plus igx. So we have this nice parametrization, and the z, we fix a z in m delta closure. This is g of x naught for some x naught in d and delta closure. Okay, so down here we have some x naught, and the corresponding point here is z, and w is parameterized. So we just sort of plug in this parametrization over here and then simplify. So f epsilon z, what does this become? So you have all these constants, and now you do this integration over the parameter space. So that's actually dn of delta naught, and then you have f of g of x times e to the minus, and then you have capital Gx minus capital Gx naught square, but I'll write it differently. So it's Gx minus x naught plus I times Gx minus Gx naught square divided by epsilon square. And now you have to be careful, because when you do the change of variables, you get, of course, dx1 wedge dxn, but you also get a Jacobian, which is just determinant of dg at x. Okay, so that's just the change of variables that you do over here, and in the end we want to take epsilon going to 0. So this is going to be some sort of dominated convergence theorem, and when you do that, you need some estimates which is where delta naught comes in. Okay, so we'll not say that. We'll just try to understand why you are recovering f over here. So the trick over here is that you let u be x minus x naught divided by epsilon, and then you just plug everything in over here, and so you have this. And let me also make another thing clear over here, that f we have now assumed is compactly supported in this region, right? So outside of this is all 0, so I can just replace this by Cn, and so I can just do this integration on Rn, it doesn't matter. And so here I get f of g x naught plus epsilon u. Up here I get minus, and what you'll get over here is epsilon u plus I times, so okay, currently seems mysterious, epsilon square, and then this, the Jacobian term is fine. And then when you do the change of variable in u, you're going to get a cancellation with epsilon to the end. So you will just get du1 dun, and this epsilon n is going to go away. Okay, so at this stage, there's one thing to keep in mind. We just want epsilon to go to 0. So what's going to happen if we put all of this together? Let me keep the picture. So the inside piece, so let's say that we can take this limit over here, whatever is happening over here. So what I get, which is why I'll write all of this. So I get Rn, I get f of g of x naught, which is just f of z. The integration is taking place in the u variable. And here I get e to the minus, when I take this limit, I get the derivative of capital G at x naught acting on the vector u whole square. Okay, and here I get determinant of dg at x naught as epsilon goes to 0. So it's only this piece that is getting integrated over here. That's the only piece that has a u. And what you use over here is sort of an exercise that's very useful. I mean, we kind of all know how these Gaussian kernels work. In one dimension, we know how to integrate it. So this piece over here, I'll just write it differently. So this is the pairing of dg acting on u, but I can also write this as dg transpose dot dg x naught u. And I think of this matrix, this is a symmetric, so this is a symmetric n cross n complex matrix over here. And there's a general exercise that is sort of worth doing once because it's very useful, that if you have Rn e to the minus au paired with au over here, du1 dun, and you have this constant, then all of this is just 1 over the determinant of a square root over here. Okay? So whatever you get out of this integration, but there is a certain, you need conditions over here, by the way. So I have not said that. What you need is that the real part of A, so this is an n cross n symmetric complex matrix. You need that the real part of A is positive definite. And remember, what was capital G for us? Capital G was I plus I times G, where dg at 0 was 0. So for some amount of time, if you take this to be capital A, because of this identity matrix over here, for some amount of time, you're going to have, I'm sorry, let me write it like this. So dg was, yes. You're going to be able to ensure this condition for some amount of time. And that is where this delta naught comes into. That's why this picture is local, because you need this positivity on A to be able to say this. And then, so this comes out, and the rest of it just gives you a 1. So all of this just becomes f at z. Okay? So yeah, I mean, I've skipped a lot of details over here, but the reason why I wanted to show you this is because this is sort of the first thing that you try to do when you try to do some sort of approximation. You try to convolve with a Gaussian kernel like this. Now, just a minor thing to keep track of over here, we are using, I mean, of course, here in this estimate, so this is just a pointwise convergence, but we want uniform convergence. And where are we really using the information about the point? It's when we are taking the limit over here, because here we go from this term to the dg term, and there the fact that g has a certain amount of regularity will help you make sure that it's a uniform estimate. That's really the only piece that you have to worry about. Okay? So I'll put sort of more details in the notes, but this is broadly the idea over here. Okay, let me pause briefly. Questions? Yes.
Just a small question, because I knew the proof with CR function. Do you remember, because I didn't know, how the CR function, how do you use CR function to prove this result?
I mean, it's exactly the same. I'm actually, okay, so one thing maybe I didn't say over here, yeah, it's exactly the same, simply because actually the function I've started with is a continuous function, right? So
CR case where, because they use exactly this kind of
it's exactly this kernel. Okay, so that appears here.
How they use the fact
Right.
that CR.
Right.
Come into the picture. You don't.
I do not immediately, you're right. It has, I mean, here it doesn't matter, it's just continuous. So this piece, correct. I do not, that's unfortunate. I should have thought about this. Yeah. No. Yeah, it's completely escaping, because the recipe is exactly the same. So yeah.
That's why I wondered how do you prove a CR function when you have a CR bundle, but no.
Right. So I mean, there in your coordinates, there's going to be an extra piece, right? This is the right. This is the TS piece, the one in your coordinates in S. So the ZZ bar piece, and that has to play off with this. So there has to be some integration by part, but I do not. Sorry, I do not remember that at all. Actually, yeah. Okay.
Both sides are complex numbers, right? I mean, the determinant might be complex, no?
This piece over here.
Yeah.
Right. Yes. Yeah.
On the right-hand side, how are you taking how do you get the square root of this? And the real part is nice because you take the square root.
It's a symmetric n cross n matrix, and I'm saying that the real part is positive. Is that not going to give me?
You're not saying anything about the complex part other than that it's symmetric.
You're not saying anything about the.
Do you expect this determinant to be positive?
Yes. Well, so even in our setting, why does that work? So if I dominate the real, sorry.
Do you need the big G or the small g?
No, I do really need the big G over there because I have this term over here. So it will really be, it will really be the big G. But what I also have, maybe this is not right, but I also can dominate the imaginary part of G by the real part. If I take the delta naught small enough, then I can probably dominate the imaginary part of dg, sorry, or this matrix over here. This matrix over here, I can dominate the imaginary part of this in terms of its eigenvalues by the real part. I think that should be the key over here. And so let me think about this, how it works for dg itself.
X near 0?
Yeah, x is near 0.
But because you have gx, g0, 0, and differential in 0
Yeah, of small g, and so this is what I have for, so this drops out.
to do this.
But at least for dg, if I look at dg transpose, this drops out, I have I and I have positive determinant here, and so for a small period of time I have positive determinant. So for dg, I think it's fine for this piece itself, because this is just identity. So for this particular situation, we are fine. Maybe the way I'm stating this is not, so let me put sort of the correct version on next time. Yeah, maybe one needs something more over here. But in our setting, it works. So let's say that we know that the determinant is positive. Then we can write this. Yeah, okay. I'll kind of verify this next time. Yeah. Any?
And it's a problem when you have some extra variable because you cannot do it because you have ZZ bar X.
Right, so this piece will not, this will have extra terms, and then I don't know how that will play that off with this over here. Because, right, so yeah, I don't remember that piece at all. I mean, this parametrization is also different over here. Yeah. All right. Yes, yes.
Then the theorem B, U, it's the intersection of all the polynomial convex contained in M.
So let me understand your question. So in theorem B, we had a neighborhood U of P in M. So we have M, we have P, and then we have this neighborhood U over here, and I'm saying U closure is polynomially convex as a compact subset in its own right. So what is the question?
U bar, you can it's equal the intersection of all the polynomial convex contained the point P.
No, I mean, no, that's not true. So you're saying that, I mean, the intersection of all polynomially convex sets containing P is just P itself. P, a single point is polynomially convex. So that's not quite right. I mean, so you're trying to construct U closure by taking some intersections, right? But that's not going to work. I mean, if you take something non-trivial and you take its hull, then you might get some hull that exits M. And this is sort of saying that there's no hull that's exiting capital M. That's the problem. And if you just take P and take all the intersections, you'll just get back P. It will not give you anything new. All right. So I'm kind of at a point where, let's see if I have any further questions. Okay, so I mean, it's sort of early, but I'm at a point where I don't want to start something new. So I think I'll just end here and start the discussion afresh in the final lecture of the day. Yeah, thank you.
Sorry.
No, it's good. Yeah, it's fine. Yeah, thanks.